Hi, everybody. Let's see you again, and let's start our classes. Our lecture number 10 today. Yeah. So, the topic of today's lecture, the optical sensor. Today, we will be continuing the previous topic as we would start previous. So, the concept of interferometry is based on the phenomenon of optical interference occurring when two waves with equal frequency coincide. The resulting amplitude or intensity varies with the phase difference between the two waves. In an interferometric sensor, such a phase difference occurs due to a path length difference between the two light beams, one of which usually follows a reference path, and the other a path of which the length is modulated by a movable part of the construction. At equal amplitudes of the individual waves, the total intensity doubles when the waves are in phase, constructive interphase, and drops to zero when in antiphase, or so-called destructive interference. If the wave amplitude are not the same, the minimum intensity is not zero, and the interference effect becomes less pronounced. The waveform of monochrome light, like say light with just one wavelength, is described by this first equation on the top of this slide. Here A is the wave amplitude for both the electric and the magnetic field component. Omega is equal to pi times f, is the angular frequency of the wave. K equals 2 pi times n over lambda is the wave number, and x is coordinate in the direction of propagation. But you should be remembered that the refractive index n over medium is defined as the ratio of the propagation speed of light in a vacuum. Speed of light in a vacuum equals c, and in the medium, v. So n is the relation between c and v, or lambda naught to lambda. In the remainder of the text, if you may find my lecture note, we assume that n equals 1, because most applications are in air having a refraction index very, very close, namely 1. When two waves with equal frequency or wavelength travel distances x1 and x2 respectively, their waveforms are described as a1 cosine in brackets omega t minus k x1 and a2 times cosine in brackets we have omega t minus k x2. Both waves fall simultaneously on the same sensor. So the wave functions are added, as you can see, for next equation here for the air total, where the equation for A from S and T looks for the next equation that we get. After for some transformation, we can get the expression for tangents B from X. And the first equations here as a total describe a periodic signal with a radial frequency omega, and in which amplitude and phase both vary with k times x1 minus x2. And hence, with the difference between the travel distance, right? Okay, so a flat wave transfers optical or electromagnetic energy into the direction of propagation, usually x direction. So the amount to s from x proportionals is y times hertz. So a quantity that is proportional to the square of the wave function. Since a photosensor responds to the irradiance, that is the average wave energy per unit area, its output is also proportional to the square of the wave function amplitude. It's like a from x, and this according to this equation. So the sensor output satisfies the next equation, as you can see here. Apparently, the sensor output changes sinusoidally with the path difference delta x. And the differential sensitivity is at maximum for odd multiples of half pi, the so-called quadrature point, and minimal and multiplies of pi. Only when both light wave amplitudes are equal, m equal 1, and resulting in an optimal interference effect. This is why the factor m is called the interference visibility. In an interferometer, the two waves travel along separate paths, one with a fixed length, the reference, and the other having a length that is set by the movable object, whose displacement has to be met. Okay? So the two waves fall on the same detector where they are effectively added up. According to the equation for the ID from the previous slide, I can show you for the second, and you can see this expression here as the finally is proportional I naught in brackets 1 plus m cosine k delta x, and in an output signal, we will get proportional to the intensity, which varies with the optical path difference and hence with the displacement of the object. And this figure shows that the output varies periodically with displacement. The unambiguous measurement range is just half a wavelength. For the red light, it's about 300 nanometers. To cover a wider range, there are two possibilities. The first is to count the number of dark light transitions during the movement starting from some reference position, as with the incremental encoder. Another method makes use of an artificially enlarged wavelength accomplished by mixing two waves of slightly different frequencies, omega, and omega or wavelength lambda 1 and lambda 2, as you can see as this equation. So R A minimum proportionals A cosine omega 1 t minus k 1 x plus cosine omega 2 t minus k 1 x. According to the simple transformation you may see in second row, we can get in this final expression. A minimum will be proportional to A cosine omega minimum t plus b sub t from x times cosine omega sub s t plus b sub s from x. And this is an amplitude modulated wave, of which the envelope has a frequency omega minimum. And equal to half the difference of the two frequencies omega 1 and omega 2. And this corresponds to a wavelength lambda equal to lambda A mix, also called the synthetic wavelength. For instance, when the two wavelengths are, suppose, 650 and 652 nanometer, the synthetic wavelength amounts of 0.44 millimeter, resulting in an ambiguous displacement range of 0.2 millimeters, where it was originally 325 nanometers. Interference is only visible with two monochromatic coherent light beams. The creation of such a pair of coherent beams starts with a single monochrome light source, for instance, a laser or laser tile. The emitted light beam is split up into two separate beams, for instance, using a semi-transparent mirror. And this figure on this slide, shows such a system known as a classical interferometer of Michelson interferometer. The beam splitter, M capital, is a semi-transparent mirror. Its transmission and reflection coefficients are about 50%. The two light beams arrive at the sensor via different paths. One runs from the source via MS and MR and back through the MS to the sensor. It has a fixed length. A second beam travels via the movable target and ends at the sensor as well. Its total path length varies with the position of the target. Evidently, all optical components should be accurately aligned to achieve a proper operation. A major disadvantage of the interferometer configuration of this figure is the optical feedback towards the source, which may introduce instability of the output frequency. In the configuration of this figure, such feedback is eliminated by using an extra beam splitter. This type of interferometer is referred to as the Mach-Zehnder interferometer. Originally designed for the investigation of the properties of transparent samples, and it can also be used for displacement measurement. Again, two coherent light waves are involved. The reference wave travels over a fixed distance via semi-transparent mirrors MS1 and MS2 in bottom, and the other reflects as a set of mirrors as the MR1 and MR2 fixed on a movable target. The other reflects at this part. So there are two receivers which can act in balance mode. When one has minimum output, the other has minimum output. The disadvantage of this interferometer is the necessity to connect mirrors to the moving target. The simplest interferometer is the Fabry-Pérot configuration, as you can see in this slide. It is essentially an optical cavity made up from two semi-transparent mirrors in parallel. The moving object is fixed to one of these mirrors. The sensor receives light that has traveled a number of path lengths in the cavity. Suppose the path length between the mirrors is half lambda. Then the waves leaving the moving mirror have phase difference of whole lambda and are added up as a constructive interference when the path length is just 1/4 from lambda. In this case, the waves have phase difference of half lambda, resulting in destructive interference. When the pitch of an incremental encoder is made smaller, in the order of the wavelength, the light is refracted at the grating. This effect is used to further increase the resolution of a linear encoder by combining it with interference. And this figure shows the basic principle of this interferometric encoder. The instrument comprises two scales moving relatively to each other at about 1 millimeter apart. One is transparent, the other not. The non-transparent scale has a pattern of small grooves with pitch equal P. And this is the step grating. The transparent one is the scanning grating with the same pitch. Light that falls on such a grating will be partially diffracted, resulting in diffracted beams of order 0, plus minus 1, plus minus 2, and so on. In this case, we only consider diffraction of the orders minus 1, 0, and plus 1. The order 0 corresponds to the non-diffracted beams. The zeroth order wave from passing the transparent grating is the step grating, where it is diffracted again in 3 directions, 0, plus 1, and minus 1. When the gratings are in line, the wave fronts have all the same phase. However, when the step grating is shifted over a distance x, the diffracted wavefront shows a phase shift equals to a phi proportional to pi times n times p over lambda. And here is the order of diffraction. The same holds for the two diffracted beams from the scanning scale. When they hit the step scale, 3 diffracted beams result with the same phase shift. The design is made in such a way that the diffracted beams interfere when entering back to the scanning scale. For each of the 3 directions, the phase difference of the interfering waves is equal to pi. Each time the wavefront passes the scanning grating, it experiences an additional constant phase shift. By design, this phase shift is pi for the 0th order diffracted waves and 0 for the other waves. Interferometry is mainly applied for linear displacement measurement. However, the interferometric sensing principle can also be used to create angular displacement and velocity sensors. Rotation measurements by interferometry require additional optics, for instance, a prism atom. Since the resolution is high, interferometry is also applied in sensor systems, where the measurement introduces only small displacement over a sensitive part. For instance, pressure, vibration, and inertial acceleration sensors. In these cases, the small displacements of membrane, a cantilever, and a seismic mass, respectively, are measured by an interferometric principle. In all these examples, light is guided through fibers to and from the sensor element, allowing the construction of very small sensing devices. As an interferometer has a very high sensitivity to displacement parameter, it requires a rigid setup and careful adjustment of the optical component. And furthermore, a frequency shift delta F induces an output change equivalent to a phase shift of 4 times 5 times delta F over C. C here is the speed of light. I hope you remember, right? So an interferometer, therefore, needs a very stable source to minimize phase noise in the output signal. Altogether, an interferometer is quite an expensive instrument. The range of an interferometer runs from several centimeters up to several tens of meters and depends on the maximal number of subsequent fringes, light-dark transitions, that can be counted. The resolution is set by that of the interference pattern measurement, either in time or in the spatial domain. The accuracy depends largely on the accuracy and stability of the wavelength, the displacement between two consecutive colors. The wavelength in air varies, but non-linearly, with the index of refraction, and hence with temperature, pressure, and air humidity. For small variations of these parameters, an approximation for the wavelength change is seen as this equation, as delta lambda over lambda proportional for these coefficients, as you see, like expression. In this expression here, delta T, delta P, and delta H are the changes in temperature in centigrade, pressure in hectopascals, and relative humidity in percent, respectively. An example, the wavelength of the helium neon laser is in vacuum is equals 0.6 micrometers. In air with temperature of 20 centigrade, pressure equals 1013 hectopascals, and 50% humidity gets the lambda 0.6, and you can see as the last values, it's a big difference from the lambda naught in micrometers, right? The relative accuracy of a non-compensated interferometer in a conditioned room is not much better than 10 micrometer per meter, hence the 10, mainly due to pressure dependence. When compensated for environmental parameters, which is, I must say you, it's never perfect, an accuracy of 3 micrometer per meter can be obtained within a temperature range from 0 to 40 centigrade. Some types of errors can be reduced using two waves with different wavelengths, and assuming the errors are common to both waves. Light travels through a medium with a peak speed v determined by its optical properties, so the m phase, LF phase time t for covering a certain distance x is proportional to that distance t equals x over v. The TOF method is based on measuring the time interval between the emission of a light pulse and the arrival time of the reflected pulse. The speed of light is high. It's about 300,000 kilometers per second in air. So the TOF of a light pulse is very short, roughly 3 nanoseconds for each meter, or 6 nanoseconds for a distance of 1 meter to a target and back. The measurement of short distances calls for vast electronics to obtain a reasonable resolution. For the long-range resolution is not a major problem. The boundary is mainly set by the decreasing intensity of the reflected light at increasing distance, and hence the reduced F/N ratio. When the incident laser light makes an angle with respect to the target's normal, the light is reflected away from the receiver. When such a situation is accepted to occur, the target can be provided with a retroflexing foil. The reflected beam makes the same angle as the incident beam, and most light will be captured by the detector. The same can be done for an absorbing target surface. And now let's start another interesting topic called interface. You know that LEDs and photodiodes are the most frequently used electro-optical components in mechatronic applications. Therefore, we give some basic electronic interface circuits for these devices. The simplest circuits are with discrete resistors and transistors, but they have rather poor stability. And on figure A, on the left part of the slide, represents an interference circuit for controlling a LED. With either E and R of the current through the LED, and hence the output power can be adjusted to a proper value. The exact value follows from the voltage to current characteristics of the device and the load line. Let's see this equation of the bottom. And figure B on the middle shows the load lines corresponding to two different values for R. And figure C shows the resistance where R is fixed and the current is adjacent by the voltage E. In both cases, the bias point is set by the intersection of the characteristics and the load line. In figure A, two possible readout approaches for a photodiode are indicated as current and voltage readout. In the first case, the circuit is loaded by a system with zero input resistance. In figure A, modeled by a resistance equal R as 0. In the latter case, the measuring system has an infinite input resistance, or R like becomes to infinity. And for a finite value of the resistance, the output voltage is given by the intersection of the type characteristics and the line of the V proportional IP times R, as shown in this figure. Clearly, only current out provides an output voltage that varies linearly with the photocurrent. And similarly, only current control over LED provides a well-defined optical output. These conditions cannot be met easily just by a resistor. Using operational amplifiers, interface circuits for both source and receiver can be designed with much better performance. And this figure shows the basic configuration for each of these components. In both circuits, as in left, as in right, the operational amplifiers are configured in the feedback mode. This makes the voltage difference between the two input terminals as 0. And hence, the voltage at the negative input terminal in figure A is equal to E, forcing a current E over R, flowing through the resistor R. And since no current flows in the input of the ideal operational amplifier, This current must also flow through the LED, generating an associated radiant flux. By varying E, namely here on the radiant flux varies accordingly. In right figure B, the operational amplifier is configured as a current to voltage converter. The photocurrent generated by the photodiode is forced to flow through feedback resistor R, producing an output voltage minus R times IPD, as you can see here, and we can measure on this part. The resistor R in another in series with the positive input terminal serve for compensation of the bias current of the operational amplifier, which flows also through the feedback resistor. An effective way to eliminate the influence of environmental light is intensity modulation. And this can easily be achieved using the circuit of the left side. The optical output power is proportional to the input voltage E. So when E varies, the intensity is modulated by this voltage. And the modulation frequency, the carrier, should be chosen such that interference signal can easily be separated from the signal by filtering. A proper signal processing makes the output of PSD independent of the intensity of the light beam. And this figure shows a combined analog to digital processing circuit for PSD signal. The currents A sub A and F sub B from the PSD, as you can see here, are converted into the voltage VA and VB, respectively. Using simple IV converter configured with operational amplifier. Next, the output voltages are converted into digital signals by two ADC. All mathematical operations according to the equation are performed by a microprocessor. The best performance is obtained when the output range of the IV converter matches with the input range of the ADC. In that case, the system takes the most advantage from the full resolution of the ADC. However, the irradiance varies strongly with distance. At large distances, the output signal may drop below the acceptable noise level. On the other hand, at close distances, where the irradiance is high, the interface electronics may run into overload. To extend the measurement range of the source intensity could be controlled in such a way that the PSD receives the highest possible radiant power, irrespective of the distance. The sum of both output currents of a PSD is proportional to the irradiance, and hence this sum is a suitable quantity for controlling the emitted radiant power of the source. And namely, figure on this slide gives an example of such a control circuit. And here the signal processing is performed by analog circuit. The output of the summing amplifier is compared with a reference voltage Vref, as we can see here on the bottom. The amplifier difference controls the current through through the light source in such a way that the sum voltage remains reference. Within the operating range of the control circuit, the summing voltage equals the reference voltage. The measurement range can be set by adjusting the reference voltage, and since the intensity of the incident beam is fixed by this feedback, the output signal is that of the differential amplifier, and the analog division can be omitted, which is an important advantage of this approach. Many integrated optical sensors can be directly connected to embedded systems. And this figure shows an example of a compact PSD sensor. This sensor uses only three connections: supply voltage, ground, and an analog pole output voltage. The output voltage varies with the location X of the reflected light source, which depends on the detected object distance as well as the physical dimensions of the sensor. Source and detector are configured according to this figure. For this setup, X proportional A times F over L. With L, it means the object distance. Here you have on a vertical line. A, the distance between the sensor and the projector. And F is the focal distance of the lens. This relation is an alternative approach to the triangulation option discussed a couple lectures ago. Note that the relation is only valid for a limited range of distance L to the object. When the object is too close to the sensor, the distance X of the reflected spot will be beyond the range of the sensor. And this relation allows a straightforward calculation for the distance of an object based on the measured voltage. Transmissive or reflective optocouples require little in terms of interfacing when they are used to detect a digital state. Methods are discussed for using operational amplifiers to create a constant current source for the emitting part and current to voltage converter for the receiving part. For binary detection of a state, such as the presence or absence of an object, often a simpler interfacing strategy suffices. For the emitting part and LED, a current limiting resistor can be used. And for the receiving photodiode, a pull-up resistor as forward bias. Also, capacitive interfacing of this sensor is possible, as discussed with the optical array sensor. The register can be chosen such that the output threshold is about 2.5 volts. When no light, it receives the output, and voltage is higher than 2.5 volts, and if light is received, the voltage is well below this value, namely 2.5 volts. Under this condition, the output can be connected directly to a digital input pin of an embedded controller. Technically, besides this comparator function, also a Schmidt trigger would be necessary in order to make sure that there is no bouncing at the transition from light to dark and vice versa. Optical sensors are used in a wide variety of applications, ranging from a simple distance measurement to complex navigation systems and object identification. The applications discussed here are categorized in this state. Major measurable attributes of linear displacement are relative position, velocity, and acceleration. Optical sensing allows the measurement of these quantities, position, velocity, and acceleration, without making contact with the moving object. Optical sensing systems are widely used for contact-free distance measurement in mechatronics. The major principles is the order of increased accuracy, reflectance, triangulation, and interferometry. The reflectance method is very useful for low accuracy applications and binary sensors. The small-sized electro-optical components can easily be mounted on or integrated into mechatronic systems. If there is not enough space to mount the sensor at the measurement location, the light can be transported to and from the proper position using optical fiber. Since reflectance depends on the reflectivity of the object, operation is restricted to environments with environment objects. In application with a variety of possible objects, accurate distance data can only be achieved after a calibration with these objects. And this problem was recognized in the early days of robotics when designing a control gripping system. To become independent of the reflectability and the orientation of the object to be handled, special algorithms and sensor configurations have been developed. These problems still exist. For instance, for medical robots and for robots for unmanned inspection and exploration of unknown areas. If objects are completely unknown, as is the case of navigation in an unknown environment, sufficient tolerances should be allowed in the obtained distance data using reflection methods. To eliminate the influence of changes in source intensity and other unwanted interference in an optical displacement system based on intensity modulation, multiple sensing and feedback are effective solutions. Adding one or more receivers to compensate for the effect of the unwanted changes makes reflection-based system less sensitive to the surface properties and may even allow uncalibrated operation. Another solution, where the relative position of transmitter and receiver is adjusted such that the maximum intensity is received. The distance is found irrespective of the surface characteristics. Feedback is an even more powerful solution, but has higher system complexity. And this figure shows an example of such a system. The light reflected by the movable target is projected onto two photosensors via a rotating mirror. The position of this mirror is controlled such that the two sensors receive equal radiation, like position X in figure A. The corresponding angle of the mirror is phi phi. Upon displacement of the object to position X, the light beam shifts from the center of the dual sensor, resulting in different photocurrents. This difference is used to drive the mirror to rotate an angle P2, as you can see on the right side, where the photocurrents become equal again. The control signal for the angle is a measure for the displacement. By feedback, the requirements to the source and the sensor are reduced significantly, as explained in uncertainty aspect. For two-dimensional displacement, the moving mirror has 2 degrees of freedom, and the detector comprises 4 receivers arranged in a square in class. The principle is applied in, for instance, automatic focusing systems in certain camera types. Another application is found in contact-free measurement of profile. Commercial instruments for that purpose are available with a resolution down to 50 nanometers and range of about 1 meter. All aforementioned examples use the change in irradiance with distance between source and sensor, usually a 1/x relation, and in light absorbing or attenuating medium, the intensity drops exponentially. According to the Lambert-Beer's law, let's look at this equation on the top, where I naught here is the intensity at a point where we have x equals 0. I from x, the intensity at the position x, and alpha is the absorption coefficient of the medium. The absorption coefficient of air is rather low. Some materials show a much larger absorption and can be used to create a distance sensor based on light attenuation. A design with a fluorescent optical fiber, very popular last time. A light source injects light into the fiber at a particular position along its line. The intensity of the light that arrives at both ends of the fiber is measured by 2 photodiodes. According to the equation, as you can see here in the slide, the intensity at each fiber and depends on the distance between the position of the light source and the photodiode. Similar to the PSD, the difference of the photocurrent is a measure for the position of the light source. The distance range equals about the length of the fiber, usually at about 88 centimeters in the experimental setup. Distance measurement over a very short range can be performed using optic fibers. And 2 different arrangements are depicted, namely in this slide. Light from the emitting fiber reflects at the target and is intercepted by the receiving fiber. The light diverges within a short distance from the exit end. So the irradiance at the entrance face of the receiving fiber depends on the distance x, in a similar way as in the arrangements of this figure. And this figure 2. With 2 receiving fibers in differential mode, most common mode interference, for instance, the intensity of the emitter is subtracted. The sensitivity characteristic depends on the angle of divergence, the standoff distance, and the angles between the fiber ends and the flat target. Since the output is an analog signal, the resolution of the distance measurement is mainly noise limited. Using modulation technique and proper filtering, the equivalent noise can be as low as 1 nanometer, proportional for the square root from hertz. A method to significantly extend the measurement range is based on 2 wavelengths. At the expense of higher system complexity, the range can be extended up to 40 millimeters. Distance measurements based on reflectance have a limited range due to the inverse power law given by our equation. And if we're using triangulation systems, and that are less sensitive to the intensity of the reflected beam if properly interpreted. In the triangulation system shown in this figure, the PSD may be replaced by a diode array, which simplifies the interfaces, but the resolution is restricted to that of the array. Commercial triangulation systems are available in a compact housing that includes laser, one or two PSDs, optical components, and interface electronics to generate an output independent of the intensity, according to this. The instrument either contains a display or provides an electrical output. Measurement ranges run from a few millimeters up to several meters. Reproducibility is in the range from ±1 to ±10 micrometers. Size reduction of the optical system is another issue to increase the versatility of distance measurement systems based on triangulation. An example of a technological solution to miniaturization where the LIGA process, German lithography, Galvanoformung und Abformung, is applied to realize the required optical structure. The total device measures 7 times 7 times 3 millimeters, so small. And obviously the measurement range is small too, about 1 millimeter. However, the repeatability error is less than 3 micrometers. An example of a displacement sensor using interferometry in combination with the feedback principle of uncertainty aspect. The system uses the speckle effect of a laser beam falling on a non-specular surface. Speckles are randomly distributed light and dark areas on the surface. This speckle pattern changes with the distance from the laser to the surface. The feedback system uses this dependency. With a set of piezoelectric actuators, the light spot on the target is controlled in such a way that it follows a bright speckle when the target is moving. In this way, the movement of the target is transformed to that of the actuator. An essential element of the system is a self-mixing interferometer, and this will be explained in the section on velocimeter. The system enables displacement measurements over a range of 500 millimeters with submicron resolution. Commercial sensing systems based on the TOF principle cover ranges from about half meters up to 10 kilometers, with an inaccuracy ranges from a few millimeters for short-range types to a few centimeters for the long-range types. The resolution is typically 1 order in magnitude better. Besides simple distance measurements, the principle is also applicable for range finding and imaging. Such systems comprise a rotating scanning mirror for one-dimensional or two-dimensional scanning of reflecting objects. Triangulation is applied in a multitude of applications where an accurate contact-free distance measurement is required. Very high resolution is needed in applications like roughness measurement and profile measurements too. In such applications, one-dimensional laser triangulation is combined with a two-dimensional scanning mechanism. A triangulation system is detected that performs the simultaneous measurement of surface roughness and surface height. It means displacement in the normal direction. The roughness measurement is based on the scattering of a light beam incident normal to the surface. The height measurement follows the standard triangulation method. A linear photodiode array is used to determine the position of the reflected light. With this system, roughness can be measured over a range from 5 to 100 nanometers. The high range amounts to plus minus 300 micrometers. Since the triangulation principle allows contact-free distance measurement, it is preeminently suitable for measuring the objects having a high temperature. An example of this application, where a system is described for measuring the flatness of hot steel plates after being pressed by air of roll. In the application, a light strip is projected under an angle of 30 degrees onto the sheet, moving at a maximum speed of 15 meters per second. A line scan camera with 2048 pixels views the strip in perpendicular direction, so it receives a light spot of about 10 pixels in width. Using a special algorithm, the resolution is increased to an equivalent of 0.1 millimeter in a eye of the steel plate. Position or displacement sensors that are intended for a very particular application may be redesigned to serve other applications in mechatronics and quality inspection. Examples are the optical mouse and the DVD pickup system. An optical mouse consisting of a LED and CMOS camera is used for measuring the viscoelastic properties of polyethylene. Experiments show that feasibility and limitations of this application. A commercial DVD pickup head appears also suitable as a basis for an optical accelerometer and a touch trigger probe. A particular application area is the exploration of an unknown environment or object reconstruction for recognition purposes. Triangulation methods used for this specific application field are further discussed a bit later in this lecture. A velocity can be derived from distance information by taking the time derivative of the displacement signal. Likewise, acceleration is obtained by differentiation of the velocity signal. So, in principle, any displacement sensor can be taken as a starting point of a velocity or acceleration measurement. Since any measurement signal contains noise, differentiation will increase the noise level of the velocity signal obtained in this way. A better option is to select a measurement principle that produces an output signal that is directly related to the speed or acceleration of the object under the test, without the need of a differentiating operation. The velocity of a vehicle, like car, train, and mobile robot, is often determined from the rotational speed of the wheel, obtained by a tachometer, for instance. Let's look at this equation here, please. And we can see in this, where n here is the number of revolutions per minute and r capital, the circumference of the wheel. The method is rather inaccurate because slip and wear of the wheel introduce measurement error. Alternative approaches adopt the measurement and correlation, both to be implemented by optical sensing. The basic operation of the correlation method using optical sensor is presented in this figure. Two sets of a transmitter-receiver pair in reflection mode are mounted at the moving vehicle at the top. And distance over d apart in the direction of the movement. When the surface is rough, the reflected signals depend somewhat on the particular structure at the point of impact. While moving, the output signal will show a random component according to the varying scattering of the surface. Both output signals are the same, but displays over a time interval d over v. The time delay between these signals can easily be derived by cross-correlation. The cross-correlation function shows a maximum for a time difference equal to d over v from which the velocity is calculated. Also, the implementation seems straightforward, but a proper result is not evident. The S to N ratio is adversely affected by vibrations or other movements like roll and pitch of the vehicle, misalignment of the optics, and surface characteristics. Moreover, a high speed required a high simple rate to obtain a reliable correlation function, whereas at low speed, the delay time is long, which necessitates longer processing time to avoid large measurement errors. Various solutions have been proposed to overcome such difficulties. On a system that makes use of optical fibers, transmitting the light from two laser tires towards the moving surface. The laser heads are 30 centimeters apart, and the distance to the surface is about 1 meter. Using a special correlation technique, the speed of the moving surface was measured up to 30 kilometers per hour with an error of 9%. Many alternative methods for contact-free velocimetry using optical means have been proposed. We mentioned just some of them here. Apart from time filtering of the reflected signal, spatial filtering is another useful approach. The moving object is illuminated by environmental lighting, so not necessarily coherent light. The illuminated area is viewed by a photodetector through a grating with small periodicity of d. When the object moves with velocity v in the plane of the grating, the output of the detector contains a frequency component equals to kV over p, with a k the optical magnification. A velocimeter is described that uses this principle. The grating has been replaced by a CCD camera acting simultaneously as detector and spatial filter device. Information about the direction of the movement is obtained by creating a quadrature signal, which is simply accomplished by a modified CCD readout system. Experiments reveal velocity errors of less than 0.1% up to velocity of 20 meters per second. Various optical velocimeters are based on self-mixing interferometers. Self-mixing is obtained by optical feedback. Part of the laser light is fed back via an external reflecting surface into the laser cavity. When particular conditions with respect to phase and amplitude of the returning light are fulfilled, the laser beam shows power fluctuations that are more or less sawtooth shaped. The fluctuating intensity is absorbed using a photodiode at the back of the laser. One of the advantages of self-mixing interferometry is the more compact arrangement of the optical paths and simple alignment. Velocimeters based on self-mixing interferometry are described in, for instance, at constant distance between the target and the laser head, the power fluctuations have a more or less constant amplitude. When the target moves with velocity v, the spectrum of the fluctuation contains the Doppler frequency f sub d. You can see here on this equation, from which the velocity can be derived using this equation. Here is a lambda is the wavelength of the emitted laser light, and phi is the angle of incidence. At moderate velocity, the Doppler frequency is rather high. For instance, using a laser with wavelength 680 nanometers and normal incidence p equals pi, the Doppler frequency at a velocity of 1 meter per second equals 2.9 megahertz. Accurate determination of this frequency is hampered by the presence of the speckle effect, which introduces multiplicative noise to the signal. Moreover, when used in automotive applications, like other movements, introduce measurement errors. In particular, fluctuations in the angle f and variation in the light above the ground may give large errors, as can seen from this equation on the top. These errors can largely be eliminated using a differential configuration. Two lasers are pointing to the ground with incident angles of plus minus 18 degrees with respect to the ground north. The Doppler frequency that can be reconstructed from the two output signals is less sensitive to car movements other than in the driving direction. Experiments with the two laser configurations showed a mean standard deviation less than 0.04% at velocities up to 100 kilometers per hour. A well-known application of the optical TOF principle is found in laser guns that measure the car speed. Usually, these systems emit a series of short pulses. From the TOF of the reflected pulses, both distance and velocity of the vehicle can be derived. Typical range and accuracy are from 5 to 500 plus minus 2 kilometers per hour. Inertial-based sensors respond directly to acceleration, avoiding the noise-enhancing differentiation of position or velocity signal. Such an accelerometer comprises a mass and a spring element, see also piezoelectric sensor. When the mass is accelerated, the resulting inertial force causes the elastic element to deform in proportion to the applied acceleration. This deformation can be measured in various ways, for instance, by optical means. However, the displacement is generally very small, and proof of measurement requires a sensor with high resolution in terms of displacement. Configurations with optical fibers in reflection mode, look like in this figure, are suitable candidates for this task. A particular solution is proposed in one publication. Here, the small displacement is measured by an incremental encoder using the Moiri effect, according to figure B. One grating is fixed to the housing. The other grating, making a small angle with respect to the first, is connected to the seismic mass. Light is conducted to and from the grating through a pair of optical fibers, transmitter and receiver, providing the measurement of the transmission, which is modulated by movement of the mass. Due to the small angle, even small displacements of the mass result in a measurable displacement of the Moiri pattern. Actually, there must be two pairs of transmitters receiver fibers to enable measurement of the direction or displacement according to the principle given in this figure. The system is used for measuring vibrations of large civil structures and has a useful bandwidth of 5 Hz. The resonance frequency of the mass spring combinations here is near the 20 Hz limit, the bandwidth, as is further explained in piezoelectric sensors. Angle measurements can be categorized in angular displacement T, angular speed or rate T, and angular acceleration. Accurate measurement of angular displacement and mostly performed by encoders, either absolute or incremental angular movement over a very small rate can also be detected using the configuration of figure A. In this case, the transmission from transmitting to receiving fiber is modulated not only by a vertical displacement, but also by rotation of the target as well. A particular application is the inclinometer or tilt sensor. It measures the angle with respect to the Earth's normal and is a useful device for working robots to control movement and equilibrium. The market offers various ready-to-use inclinometers, covering ranges from ±1 to ±90 degrees, with excellent linearity. The mechanical types are based on a free-moving pendulum that always points downward, also when the housing makes an angle P with the Earth's north. At the pivot of the pendulum, some means of displacement sensing is connected, which gives an output signal that is related to P. This can be a simple optical displacement sensor, is reflected or transmission mode by an encoder or a vane connected to the other end of the pendulum. Application of feedback loop reduces error due to, for instance, a strong nonlinear relationship between angle and measured displacement. The proximity sensor is also sensitive to angular displacement of the reflecting surface. This concept is further detailed, and the fiber optic angular sensor is composed of a rotatable mirror, one central input fiber, and 4 output fibers. The configuration combines a high angular sensitivity and a negligible sensitivity to normal displacement. I think it's enough from this part of the lecture. I'm just show you a bit after a small break. Okay, so I'm just